So far, we have seen CNNs do one thing really well. They can shrink images, and in the process capture local and hierarchical patterns. Convolutions, pooling, strides, all of them reduce spatial resolution so that the model can learn higher level features. See, that works great for image classification. But classification isn't the only computer vision task. Sometimes we don't just want a classification label, right? We want to know where things are inside the image. That means the model has to go back from compact feature maps created by convolutions, pooling layers, to something that looks like the original image. So the big question is, how does a CNN rebuild the spatial structure after it has been compressed? That's exactly what Conv2D Transpose layers are designed to do, and we will learn all about them in this video. So Conv2D Transpose layers. So what are these? So think of them as a reverse of the regular convolutional layer. Okay. So what is the reverse of a regular convolutional layer? Let me explain. First, let's talk. Let me take a simple input, very small input image. Let's say 2x2 pixel. Okay, and let me explain. So the input pixels are just 2x2. Filter is also 2x2. Okay. So input pixel values are say 1, 2, 3, 4, and the filter values are 1, 0, 0, 1. I've just chosen some random values here just to explain to you the Conv2D transpose operation, what happens. Okay, so what we do is we take each element of the input pixels and we multiply by the filter. So let's take 1. So what is the first element here? The 1. Let's take this 1 and multiply 1 with this filter value. So if you multiply 1 with this filter, you'll get 1, 0, 0, 1. Again, I'm going to choose a case of stride equal to 1. So for stride, I'm going to explain what this is. For stride equal to 1, okay. So I'm just taking this 1, the input pixel in the input, the first pixel, 1, and I'm going to multiply this to the filter. So 1 multiplied by this 1, 0, 0, 1 is basically this. Next, I'm going to take this 2, right, in the input, the 2, and multiply that with the filter values. I'm going to get 2, 0, 0, 2. Make sense? Okay. Now I'm going to take this 3 value and I'm going to multiply with the filter. Okay. So I'm going to get 3, 0, 0, 3. Okay. Then I'm going to take 4 and multiply with the filter. I'm going to get 4, 0, 0, 4. Okay. Now stride equal to 1 means, again, the filter moves just one window, right? It will just move one window. That's what I said stride equal to 1 means. So when you have stride equal to 1, what it means is, now if you look at this top row, the top values here, again, whatever is colored in this orange, so you add them up. So you add 0 to 2, 1 to 0. Okay. So you do that. So what happens is now your output would be 1, 2 plus 0, 2, 1 plus 0, 1, and the final values are 0, 2. You do the same thing with the bottom cells here. Okay. So you take 3, 0 would be the same. 3, 0, but 0 plus 4 is 4, 3 plus 0 is 3, 0, 4. Okay. Now, what we're going to do is we're going to take these two, again, orange or, orange colored cells here or rows here. We're going to take these rows here and we're going to add them up and we're going to produce our final shape. So 1, 2, 0, the top row remains the same. 0 plus 3, 3. The second and third row, we're going to add them up. 0 plus 3 is 3. 1 plus 4 is 5. 2 plus 0 is 2. And then 0, 3, 4. So this is your convolutional 2D transpose operation. So basically what happened is we took an input shape of 2x2 pixels. We upscaled it to an output shape of 3x3 pixels. That's one of the main functionality of the Conv2D transpose layer. See, regular convolutional 2D layer, right? If you don't use padding as same, the goal of regular convolutional 2D layer is to downsample. So your input image shrinks after you do the convolutional 2D operation. But if you do Conv2D transpose operation, your input shape can be upscaled. Okay, so that is one of the main advantage of this Conv2D transpose layer. Okay, so what you are seeing here with the stride equal to 1. Let me explain with stride equal to 2. Again, let me take the same input shape 2x2, a filter also 2x2. Okay, I'm going to do the same thing, multiply each element of the input with the filter values, and I'm going to populate it here. Okay, all right. Now I'm going to say for this is going to be stride equal to 2. So if stride equal to 2, my filter is going to move 2 consecutive windows, right? So not just one. So it's going to, because it's going to move 2 consecutive windows, there is nothing to add here. Okay, so what happens is you simply take 1001 2002 and then here 30400304. So there's nothing to add here, and then finally you just stack all this thing together, and this would be your stride equal to 2. Stride equal to 3, imagine you moving down 3 windows and you're going to have some extra zeros which you have to populate here, and your output shape will be much more bigger. So if it's stride equal to 2, your 2x2 input image became 4x4 output. So this is again the advantage of Conv2D Transpose layer. Think of this as a reverse of the regular convolutional 2D layer, and main use is whenever you want to upscale your input images to a bigger size, you use the Conv2D Transpose layer. Okay. Again, if you want to calculate these formulas, what exactly the formulas, to calculate this output shape when you use Conv2D Transpose layer. Again, these are the equations. I'm just putting it here. You can refer to them, later when you are building your own models. And if you use a Conv2D Transpose layers, and if you quickly want to calculate, these output shapes, again, these are the formulas you can use. Okay. All right. So this is about Conv2D Transpose layers. But again, why do we use them? Main reason is to upsample. It's like a reverse convolution. The goal is to increase the spatial dimensions of your input feature map. It balances out the downsampling. Right? Typically, in some of the problems, right, we use max pool or stride. When you do that, your input shape shrinks. Now, for some applications like semantic segmentation, you want your input shape to go back to the original shape. If you want that, you should use Conv2D Transpose layers. So again, as I explained, Conv2D Transpose layers, it can be used for semantic segmentation, and there are some other applications or tasks like, you can use it for, GANs, generative adversarial neural networks, decoder networks, and all that. So that's the intuition behind Conv2D Transpose layers. They're not magic. They're simply how neural networks learn to grow spatial structure back after earlier layers compressed it. So this idea is foundational for tasks like image segmentation, decoder networks, and even generative models, as I've already indicated. In the next few videos, we'll see how deep networks can stay trainable even as they get larger and deeper because of problems like vanishing gradients and the techniques as to how to fix them. If you're new to this channel, please make sure to check the full deep learning playlist. Again, you can see the link in the description, and I will see you in the next one. Happy learning.